All right, let's talk about a math problem that seems completely broken. I mean, what is 0 divided by 0? For ages, this question was a total dead end. But the answer, which came from the heart of calculus, literally changed everything.
So, to really get a handle on this whole 0/0 thing, we've got to go way back. I'm talking ancient Greece. Because this story doesn't start with some complicated formula. Nope. It starts with a brain-bending puzzle about a race that, logically, should never end. You've probably heard of this one, Zeno's paradox of Achilles and the tortoise. The idea is that Achilles, this legendary, super-fast hero, could never, ever catch a slow little tortoise if he gave it a head start. Now, on paper, the logic seems kind of airtight, but we all know that's just not right, right? I mean, of course he catches the tortoise. So what gives? Where does the argument fall apart?
Okay, let's walk through Zeno's thinking step by step. So, Achilles has to get to where the tortoise started. Easy enough. But wait, in the time it took him to do that, the tortoise has already moved a little bit forward. Okay, so now Achilles has to cover that new, smaller distance. But you see where this is going, right? By the time he does that, the tortoise has moved again. It just keeps happening. It's this endless series of smaller and smaller gaps, which logically means Achilles gets closer and closer forever, but never actually catches up. It's wild.
So, hang on to that idea. This infinite chase, this impossible task. Now, let's jump forward a couple thousand years. We're leaving the racetrack behind and heading straight for a mathematical wall that feels just as impossible to get past.
Think about this for a second. When you're driving, you glance down at your speedometer, and it says you're going 60 miles per hour. That's your speed at that exact instant. But how does that even work? How can you possibly measure your speed in a single moment, an instant that has, by definition, 0 time? Well, we all learned the formula in school, right? Speed equals distance divided by time. But here's the problem. If you try to apply that to a single instant, well, in 0 time, you travel 0 distance. The time elapsed is 0. The distance covered is 0. And that brings us face to face with the big one, 0 divided by 0. Now, in any math class you've ever taken, you were probably told you just can't do that. Dividing by 0 is a huge no-no. It's undefined. So, does that mean instantaneous speed is just nonsense? Is it something we can't actually calculate?
Well, here's where things get really cool. In calculus, 0/0 doesn't mean stop, you failed. It's called an indeterminate form, and that's really just a fancy way of saying, the answer isn't clear yet. We need to be more clever about this. It's not a stop sign. It's a signal to grab a different tool from the toolbox.
So what's this special tool? Well, it's a completely new way to think about the problem. It's a concept that stops asking, where are you right now, and starts asking, where are you headed? And that idea is called the limit. It's pretty much the bedrock of all of calculus. And I just love this way of thinking about it. A limit is like a mathematical microscope. It lets us zoom in, and I mean really zoom in, on what a function is doing right around a problem spot. So instead of trying to land perfectly on that one instant and getting the 0/0 error message, we look at the trend. We look at the path the function is taking as it gets closer and closer and closer. This is the big shift in thinking, right here. The old question was, what's the value at this exact point? And the answer was, we don't know, it's 0/0. The new question, the limits question, is what value is the function getting close to as we get near that point? We're no longer focused on the destination, but the journey towards it.
So here's the core idea in a nutshell. When we talk about a limit, we're saying that as our input, x, gets ridiculously close to some number, say a, the output of our function gets ridiculously close to some value, let's call it L. And here's the kicker. The function might not even exist at a. There could be a hole there, but it doesn't matter. With limits, all we care about is what it's approaching.
All right, theory is great, but let's see this thing in action. Let's take this new mathematical superpower and go back to that 0/0 problem that stumped us before and actually solve it. Okay, here is a textbook example. We want to find the limit as x gets close to 2 for this function. Now, if you do the old school thing and just plug in 2, well, on top you get 2 squared minus 4, which is 0, and on the bottom you get 2 minus 2, which is also 0, and boom, there it is again, our old friend 0/0. But watch this. A little bit of high school algebra is all we need. That top part, x squared minus 4, that can be factored into x plus 2 times x minus 2. And would you look at that? We have an x minus 2 on the top and an x minus 2 on the bottom. That's the part that was causing all the trouble. We can just cancel them out. And what are we left with? Just this simple little function x plus 2.
So now we can ask our limit question again. What happens to our new simplified function, x plus 2, as x gets closer and closer to 2? Well, it gets closer and closer to 4. And that's it. That's the answer. An exact, clean number that was just hiding inside that messy 0 over 0 form.
Now, I know what some of you might be thinking. Hold on a second. Isn't that cheating? You totally changed the function? But it's not cheating, and here's why. The original function and our new one, x plus 2, are exactly the same everywhere. Everywhere, that is, except for that one single problem spot at x equals 2. And remember what we said? Limits don't care about that one specific point. They only care about the approach. So for our purposes, the limit is identical. And believe me, this isn't just some neat party trick from math class. This whole way of thinking, of finding precise answers by looking at the approach instead of the destination, it's basically the engine that runs our entire modern world.
Think about it. The derivative, that instantaneous speed we were trying to figure out, it's defined with a limit. The whole concept of a smooth, unbroken curve in math, that's defined with limits too. And oh yeah, it finally puts Zeno's paradox to bed. Calculus shows us how an infinite number of smaller and smaller steps can actually add up to a finite distance. So yes, Achilles absolutely catches the tortoise, because all those infinite tiny moments add up to one single finite point in time. And this stuff is everywhere in the real world. Seriously, engineers are using limits to figure out the exact stress a bridge can take as a load approaches its breaking point. In medicine, they're used to model how a drug's concentration in your body approaches a certain level over time. Even in economics, they're used to calculate things like marginal cost, the precise cost of making just one more widget.
So if you take away one thing, let it be this. A limit is not some fuzzy guess. It's not an approximation. It is the one single exact value that a function is zeroing in on. It turns out, by focusing on the journey, we can find the exact destination, even when that destination itself seemed impossible to reach. And that kind of leaves you with a bigger thought, doesn't it? This whole idea that you can solve a problem by focusing on the approach instead of the final point, that feels like it applies to way more than just math. It really makes you wonder, what other impossible problems in our lives could we crack if we just learned to change the question we were asking?